Okay, good morning. So today we will discuss about the interface boundary conditions and fluid particle shapes. Okay, so we have discussed about the governing equations and we obtained that governing equations are nothing but in the form of partial differential equations. Okay, so once we have partial differential equations, then in order to solve the partial differential equations, what we need to do? We need to also apply the boundary and initial conditions. Okay, and in case of single phase flow, most of the boundary conditions are clear to us. So for example, if we talk about flow through a pipe, then what we do, we take the axisymmetric simulation domain, and in this axisymmetric simulation domain, if we have to specify some boundary, so this will be my axis of symmetry and this will be the interface close to the pipe wall, and here it can be given as outlet and this can be inlet. Okay, so if for this simplified situation you have to give the boundary condition, how you can specify? So there are different ways to specify boundary conditions. Let me choose one of the way. So what I can do, I can supply Dirichlet boundary condition at the inlet. What is the meaning of this boundary condition? I will be telling that at inlet, say value of velocity is something Vi, which may be anything 1 meter per second, 2 meter per second, 3 meter per second, like that. Okay, so this is the meaning that at inlet I have specified the constant value of the velocity. Typically for this type of situation, pipe flow situation, when we have velocity inlet condition, then corresponding to outlet, majorly we specify the Dirichlet condition for pressure. Okay, so if we have velocity inlet, then typically we specify pressure outlet. We can specify other conditions as well, but just one set of conditions I am trying to describe over here. Okay, so at P outlet, if I have to give the Dirichlet condition, I will be specifying some value of pressure at the outlet as PO. Okay, after that at the wall I have to specify the condition. So we know that close to the wall, what we will be having? We will be having the no slip condition. So because of the no slip conditions, I can specify that value of velocity at wall, and at wall I can define velocity in two ways. One can be parallel to the wall in tangential direction, and other can be velocity normal to the wall. So no slip condition tells that velocity parallel to the wall will be equal to 0. So tangential velocity equal to 0, this comes from no slip condition, and normal velocity equal to 0, this comes from the impermeable boundary condition. Okay, for example, this is a solid pipe wall. So if it is a solid pipe wall, fluid cannot penetrate through it in the normal direction. So that's why from there we can say that velocity at the wall in the normal direction will be equal to 0. Now comes the axis of symmetry. Okay, so can you tell me what type of condition will exist at axis of symmetry? We know that in a pipe, how will be the velocity profile? Parabolic. So profile will be symmetric about this axis. Yes, so if I consider this vertical direction to be y, then in that scenario, what I will be getting? I will be getting that at axis D, V in tangential direction, because we can also have two components. So we are considering the component which is parallel to the axis. So dV in tangential direction divided by dy will be equal to 0. Okay, this is coming because of the symmetry condition, and this we will be calling as our Newman boundary condition. Okay, is this one clear? Because here gradient of the variable we are specifying. So we all know about, say, boundary conditions in case of single phase flow. Now what about multi-phase flow? So in case of multi-phase flow, what addition is there? If you simply consider this type of pipe flow, then you do not have only the single fluid flowing inside. You may have in some portion fluid 1 and in some portion you may have fluid 2. And if you have this type of separated flow situation, then you will be solving separate set of equations for fluid 1 and fluid 2. So if you are solving this type of separate set of equations for fluid 1 and fluid 2, in that scenario what will happen? In that scenario, of course, these three boundaries, along with these three boundaries for fluid 1, this is also acting as one of the boundary, and for fluid 2, along with the outside boundaries, one internal boundary is also existing. So this internal boundary is nothing but my interface. Okay, so it means that I should know what type of boundary condition I have to apply at the interface. Okay, so we will be now talking about BCs at interface. And of course, our whenever we will be solving the generalized multi-phase flow situations, we have to solve it for conservation of mass, conservation of momentum, and conservation of energy. So it means that we have to also supply the boundary conditions in terms of mass, momentum, and energy. Okay, so let us first talk about boundary conditions for mass. So what I can do, I can assume that this is my interface, and on one side of the interface I have liquid, and on other side of the interface I have vapor. Is this one clear? Now let us assume that this is my origin, and with reference to this origin the position of the interface is Zi. Okay. Now whenever the flow will be evolving with space and time, interface position will not remain constant, it will keep on changing. So let us assume that this interface position is a function of time, because this interface position can change. Now what I will be doing, I will consider a control volume of infinitesimally small size at the interface. Now in this interface, what will be happening? Let us consider that the density of liquid is rho L and density of vapor is rho V. Okay, and if I assume that the velocity of the liquid, so this particular direction I am pointing as the normal direction to the interface, and this direction I am considering as tangential direction to the interface. Okay, so I can represent it with symbol T. So normal to the interface, this is my N. Now if I consider that WLN is the velocity in the normal direction to the interface. Okay, and so like this, and WVN is the velocity of the vapor in the normal direction to the interface. Is this point clear? What I have assumed? I have considered that normal to the interface velocity of liquid is WLN and normal to the interface velocity of vapor is WVN. Okay. Now another assumption is interface is of infinitely small size. So whatever the control volume I have drawn at the interface, this is infinitely small size. Now if you consider that interface is changing its position with time, what will be the velocity of the interface? So velocity of interface will be dZi by dt. Okay, Zi is interface position as function of time. So divided by dt will be giving me the velocity of the interface. If I consider that liquid is approaching towards the interface with velocity WLN and interface is moving at velocity dZi by dt, what will be the mass flux of the liquid towards the interface? It will be nothing but density of liquid into WLN minus dZi by dt. Similarly, the mass flux of the vapor will be rho V into WVN minus dZi by dt. Okay, so this will be the mass flux of the liquid entering to the interface and leaving the interfacial control volume. Now if I make one assumption that interface does not, or interfacial control volume does not have any mass change with time. It means neither this interfacial control, because right now for doing my analysis I am considering the interface to be of infinitely small sized control volume. But when we will be looking at the macroscopic level, interface will not be only a 2D surface. It will not be a 3D volume, but at macroscopic level it will be only a 2D surface. So at that 2D surface there will not be any storage of the mass. Okay, so if we impose this assumption or this condition, then ultimately I can say that whatever the mass is entering to the interfacial control volume, same mass will be leaving from the interfacial control volume. So it means in this scenario I can write that rho L WLN minus dzi by dt has to be equal to rho V WVN minus dzi by dt. Is this one clear? So this will be the mass balance condition across the interface. Is this one clear? So this is nothing but our mass balance condition across the interface. Now let's talk about momentum. Okay. So when I will be considering the momentum, I have to separately consider momentum in the direction normal to the interface and in the direction tangential to the interface. Okay, because momentum is nothing but a vector quantity, so it will be directional dependent. So it will be having dependence on normal direction as well as the tangential directions. Okay, so let us first talk about the balance of momentum in the direction normal to interface. So this is my interface again, okay, and this is my control volume. And in the similar way, this is my normal direction and this is my tangential direction. Now can you tell me what will be the mass flux which is entering to the interface? We have just now calculated rho L WLN minus dzi by dt. So this is the liquid mass which is entering towards the interface, and this is coming with how much velocity? WL. So when this mass is multiplied with velocity, it will be becoming now the momentum flux entering to the control volume in the normal direction. Okay. Likewise, momentum flux which is leaving out of the control volume in normal direction, it will be rho V into WVN minus dzi by dt into WVN. Okay. Other than that, we know that in the normal direction, from this side I will be having liquid pressure PL, okay, and from this side I will be having vapor pressure PV. Is this one clear? And we also know that here at this interface, this sigma will induce some force, okay, and this sigma can have two components. One component will be in the normal direction, okay, because of force, because of surface tension. So let me write it as F sigma, and one component will be F sigma n and other component will be F sigma t. Is this one clear? Okay, so surface tension force will act parallel to the interface, and in normal and tangential direction its component will be giving the corresponding constituents of the surface tension force. Okay, now anything else we have left? We know that in case of fluids, there can be some contribution of the what? Some contribution of deviatoric normal stress also. Okay, what is deviatoric normal stress? So whenever we write shear stress tensor tau, deviatoric stress tensor tau. So we have tau ij. Here comes tau 11, here comes tau 22, and here comes tau 33. So all the components which are involving 1, 2 and 1, 3, these are the shear components. Here also I will be having shear components likewise. But the components which are here, force acting on a plane and that is acting in the same direction as that of the plane. So that will be nothing but a normal force. Okay. So we do have some contribution of normal forces because of the viscous effect. But typically we know that the normal stress which is caused by normal deviatoric stress which is caused by viscosity is having very less magnitude in comparison to the pressure. So that's why majority of the time we neglect this contribution. Is this point clear? All are clear with this idea? So even in the single phase flow also, if we have to do force balance in this direction, we have to consider the component of the deviatoric stress. Okay, but this component of deviatoric stress in the normal direction is relatively very small in magnitude in comparison to the pressure. That's why majority of the time it is neglected. So that particular component I am not considering in this force balance. Okay. Okay, now what I have to do, let me consider that this direction towards the positive end is my positive direction. Okay, so now what I have to do, if I see over here, then I will be getting PL is positive, P vapor is negative, so PL minus PV has to be equal to rho L into WLN minus dZi by dt into WLN minus of rho V into WVN minus dZi by dt into WVN. And along with this, I will also be having the contribution of the which force? F sigma n. Is this one clear? So F sigma n will be coming as the another force. So what we are doing over here, P is pressure. It is not good. Because I am not dividing with area, because over here whatever this quantity I am writing, this is also momentum flux, momentum per unit area. Okay, so in the right hand side, what is this first term? First term is, what is first term? First term is mass flux, mass per unit area. So when mass per unit area is multiplied by velocity, it will be becoming momentum flux. Is this one clear? So it is already in the flux form. That's why area I am not considering over here. Now, what will be F sigma? So this other terms will be remaining as it is, but F sigma n we already know is nothing but equal to sigma times 1 by R1 plus 1 by R2. All are clear with this point? What is surface tension force in the normal direction? Surface tension force in normal to interface is always sigma times mean curvature. Okay, and what is that mean curvature? 1 by R1 plus 1 by R2. Is this one clear? So that's why F sigma n will be sigma into 1 by R1 plus 1 by R2. All are clear with this point? Now, in some of the situations you will be finding that the incoming momentum and outgoing momentum difference is very small in comparison to the pressure forces. Okay, so though this is the detailed equation in normal direction, but if the difference of incoming and outgoing momentum are small. In that scenario, we will be finding that PL minus PV will be simply equal to sigma into 1 by R1 plus 1 by R2. The way we see in case of curved interfaces. Okay, for example, drops, bubbles and other geometries. Okay. So if you do not have significant momentum across the interface in the normal direction, if that momentum is small, in that case PL minus PV will be simply equal to sigma times 1 by R1 plus 1 by R2. All are clear with this point? So this is our momentum balance in normal direction. Now we have to do the momentum balance in which direction? Tangential direction. Okay, so what we will be having, again this is my normal direction, this is my tangential direction. Now I have to consider all the components in which direction. I have to consider in tangential direction. Okay, so first thing is, what was my mass which was entering? Rho L into WLN minus dZi by dt. This is the mass flux. But now, because we have to consider the mass flux, momentum flux in which direction? Tangential direction. So we have to see if this mass flux is moving in tangential direction with some velocity, some tangential velocity W LT. So WLT is the velocity of this mass in which direction? Tangential direction. Then it will be becoming momentum of liquid in the tangential direction. Likewise, rho V into WVN minus dZi by dt times WVT. This will be the momentum of the vapor in the tangential direction. Other than this, what I will be having? We know that in the tangential direction one important term comes, which is nothing but shear stress. Okay, so let me consider tau L is the shear stress in tangential direction, particularly in liquid side, and tau V is the shear stress in which side? Vapor side. Okay. Anything else? Just now we have seen that when this surface tension will be acting, one of its component will also be coming in the tangential direction. So we have to consider one component of the surface tension F sigma T. Is this point clear? So here also there will be some F sigma T. All are clear with this point? Anything else we are missing? Okay, so if we are not missing something, now what we have to do? We have to again do the balance. So if I do the balance, then I will be having tau L minus tau V. These are acting in opposite direction. Okay, equal to rho L into WLN minus dZi by dt times WLT minus of rho V into WVN minus dZi by dt into WVT. Okay, and now comes one important thing. Now you can see over here, if this is the interface, this F sigma t and this F sigma t. If we assume that surface tension over the complete interface is constant, then the contribution of F sigma t and F sigma t will be, it will be deleted, it will be 0, okay, because it will be balancing each other. But if I assume that at this point I have different value of surface tension, at this point I have different value of surface tension, then what will be happening? Like if I have variation of surface tension along the interface, then if F sigma t is the surface tension force at this point, at other point this will be F sigma t plus some dF sigma t. Is this point clear? Now what this dF sigma t will be contributing, so say if F sigma t is equal to sigma times what? Mean curvature K, okay. Then here, and of course we have to consider its component also. Then in this direction, this dF sigma t will be including the contribution because of del sigma by del t. All are clear with this point? What I am trying to say is, what we generally do, if I define that del sigma t by del t is the rate at which sigma is changing along the tangential direction in the interface, okay, then this rate of change of sigma will be actually leading to my force difference between this point and this point. All are clear? Because if say at this point my value of surface tension is sigma, then at this point value of surface tension will be sigma plus del sigma by del t into, if dt is the distance from this point to this point, okay. And when I will be doing the balance of this minus this, then ultimately I will be finding that my surface tension force will be contributing in terms of del sigma by del. All are clear with this point? Okay. So please remember this thing. This t is not time. It is not time. I think I have done a mistake in choosing t for tangential direction. Consider this t to be as tangential direction. So it means it is a, what is this? It means this is a spatial parameter. Okay, so now we are taking the spatial derivative of, surface tension with surface tension coefficient. Okay, it is not the time derivative.
It means like t have a unit of in distance.
Distance, yes. Okay, all are clear with this point? So if there is gradient of surface tension existing, then I will be having some additional force. If the surface tension value is constant, then of course del sigma by del t will ultimately be coming out to be equal to 0. Is this one clear? Now, another interesting point is, at the interface, immediately at the interface, what we have? One side we have liquid, other side we have vapor. Okay, and at interface, molecules of liquid and vapor will be so mixed with each other that the tangential velocity of one type of molecule will induce same amount of tangential velocity in other type of the molecules also. Okay, so at interface one more condition can exist, which is the condition of no slip. If no slip condition is existing at the interface, in that scenario WLS will be equal to WLT will be equal to WVT. Is this point clear? So velocity of the liquid at the interface in tangential direction has to be equal to velocity of the vapor in tangential direction. Okay. So typically, if I consider that I have water, and over the water if wind is flowing, So how velocity profile will be there? This is the stationary pool of water. Over this, if wind is flowing, I will be finding at this point wind velocity will be 0, and above than this it will keep on increasing. So typically at the interface also no slip condition exists. Okay, at the interface between the multiple fluids. So that is the reason at the interface, because of the no slip condition, I can say WLT equal to WVT. So if WLT equal to WVT, and this whole term is also equal, that we know from our where mass balance across the interface. So from mass balance across the interface, this term is equal and this term is equal from the no slip condition. So this difference will comes out to be 0. So ultimately I will be finding that tau L minus tau V will be equal to minus delta sigma by delta T. Is this one clear? Now if I assume that I have pure interface with no gradient of surface tension, in this scenario what will be happening? Del sigma by del T will be equal to 0 and tau L will become simply equal to tau. So in tangential direction, shear stress in the liquid side has to be equal to shear stress in the vapor side. Okay, if there is no gradient of surface tension. Now, what will be tau liquid? Mu times mu liquid times del W liquid, okay, in which direction? Say normal direction. If I am taking it in normal direction, then gradient has to be taken in which direction? Tangential direction plus del W LT divided by del Z, N or Z. Okay, is this one clear? And this will be at Z is equal to Zi, and this liquid will be equal to mu vapor into del WVN by del T plus del WVT by del Z at Z equal to Z. Okay, so shear stress in the liquid side is equal to shear stress in the vapor side. Is this one clear? Now you have to remember one thing. How many tangential direction a real interface will be having? Principal tangential directions. So whenever we study about the momentum equation, how many components of momentum equation we have? 3 components. Till now, how many we discussed? 2. Okay. But whenever I will be considering a real 2D surface, it will be having 3 components. So for real 3D surface, what will be happening? Say if this is my 3-dimensional interface, 2-dimensional interfacial surface, then this will be one normal direction, this will be one tangential direction T1, and this will be another tangential direction. Have you understood? So this is normal. One tangential is in one normal side and other tangential is in another 90-degree angle. Okay, and parallel to the interface. So the way I have done this momentum balance for T1 direction, similar momentum balance will also be existing in the T2 direction. Have you understood? So for a real 2-dimensional interface, what will be happening? Earlier what I have done, I have simply represented the interface with a line. But in reality, interface will be a 2D surface. So if it is a 2D surface, it will be having 2 principal tangential directions. Okay. So as it is having 2 principal tangential directions, whatever the balance now I have presented, if it is valid along T1 direction, then similar balance of the momentum you have to apply along T2 direction. Is this one clear? All are clear with this point? So we are done with momentum balance. Now let us talk about energy balance at the interface. Energy is a scalar quantity. So again, now we will be having only single equation for energy balance. Okay. Okay, so can you tell me what will be the mass flux at the inlet? Rho L W ln minus dzi by dt. Now, whenever some mass comes at the inlet, it carries certain energy. Okay, so let us consider that small el is the energy carried by this. Okay, and the vapor leaving from where will be rho v wvn minus dzi by dt, and let's consider that energy carried by this is E. Okay, now what will be EL and EV? EL has to be equal to no. EL has to be equal to internal energy of the liquid UL plus kinetic energy of the liquid half of VL square plus potential energy. Okay, so let us consider interface is in the same orientation, so only internal and kinetic energy. If you have to consider, you can consider this also, no problem. So ZL as the potential energy. Okay, and EV will be similarly UV plus half of VV square plus ZV. Now, what will be VL and VV? VL is the total kinetic energy of the liquid. Okay, so if it is total kinetic energy of the liquid, this V has to be equal to the total velocity field. Okay, so total velocity field will be square root of velocity field in normal direction. In normal direction, velocity field will be W ln minus dzi by dt square plus velocity field in tangential direction. So first tangential direction, say it is WL T1 square, and second tangential direction it is WL T2 square. So this will be my total velocity field. Is this one clear? Likewise, you can write the velocity field for the vapor also, that I am not writing over here. Okay. Along with that, you may have some heat flux which is acting at this liquid side. Okay, so heat flux acting at the liquid side is say Q double dash L, and heat flux which is acting at the vapor side is say QV double dash. All are clear with this point? So QL double dash is the heat flux at liquid side, QV double dash is the heat flux at the vapor side. Now I can write this energy balance. Okay, so what will be the energy balance now? Q double dash L minus Q double dash V has to be equal to rho L into WLN minus dzi by dt into what? EL. Let me write at the moment it as EL only. Okay, plus minus rho V into WVN minus dzi by dt into EV. All are clear with this point? So this we will be having energy balance at the interface. Now I can assume that if near the interface, okay, interfacial layer, because of the no slip condition, is having very less interfacial slip, then close to the interface I can assume that heat flux can be approximated in terms of the Fourier law, assuming that the gradient of the temperature is actually known to us. So if gradient of temperature is known to us, then I can write KL into dt by dN, because this heat flux we are calculating in the normal direction. Again, heat flux is a vector quantity. Okay, so it's a direction dependent. So this heat flux we are calculating in which direction? Normal to the interface. So normal to the interface, whatever heat flux will be there. So KL dt by dN in liquid side at Z is equal to Zi, and this vapor can be written in terms of kV, thermal conductivity of the vapor, into dt by dN in vapor side at Z is equal to Zi. Okay, so this will be towards vapor side, this will be towards liquid side. Are you clear with this point? So this will be representing nothing but my energy balance at the interface. Now of course this energy balance we can try to formulate it in different ways, and we can further simplify it. But at the moment I am keeping it in the generic form. So depending upon the requirement, wherever it is needed in whatever form, that we will try to derive from this generalized part. Okay. So this is about the boundary conditions at the interface. Now one more thing you have to remember over here, like in mass balance we assumed that interface is not storing any heat. Here also we have assumed the similar thing. Whatever net flux of heat is from the energy coming from liquid and vapor side, that is QL minus QV. So it means interface is not storing any heat. If interface is storing heat, then we have to add one more term as mass of interface into dt by d. So that we are not considering. Okay. Okay, now let's talk about shapes of fluid particles. Okay. So typically whenever fluid particle will be existing in different situations, these can have different shapes. So over here first we are discussing the shape of the fluid particles when they are coming in contact with the solid surfaces. Okay, so if I have a solid surface and gravity is acting in this direction, and on this solid surface if I have dropped a liquid volume, then this liquid volume, if it is of smaller size, it will be taking this particular shape. Okay, and this particular shape is known as sessile drop. A droplet of liquid which is resting on a solid surface, that is called as sessile droplet. Likewise, if you reverse the situation, you have an inverted solid surface which is placed over a liquid pool. So here everywhere you have liquid, and from the top you have a solid surface. Now in this, if you have any air bubble, that air bubble, whenever it will be coming in close contact with the liquid surface, liquid pool near the solid surface, it will be forming shape something like this. So it will be resting on that particular solid surface. So again, this bubble is now resting on the solid surface, so I will be calling it as sessile bubble. Okay, all are clear with this point? Another situation I have taken the same situation, sessile drop, but after that I have inverted the solid surface. Okay, now because of the gravity, what will happen? Whatever the liquid volume is attached, that will try to elongate in the downward direction. Okay, so that elongated liquid volume is something which is called as pendant drop. Okay, so a liquid volume hanging from a surface is what we are calling as pendant drop. Now another situation could be, I have a solid wall, and in the surroundings of this solid wall everywhere I have liquid, and here I am having one air bubble which is attached to this solid wall. What will happen? Air bubble will be having low density. Because of its low density, it will try to rise in upward direction. Whereas the surface tension force, which is actually making its contact with the surface, it will try to keep it close to the surface. So because of that balance, it will try to take this type of shape, which is called as pendant bubbles. Okay. Third situation could be where three different fluids are involved. Here I am having some fluid rho 1, here it is rho 2, and here it is rho 3. And in these three different fluids, say rho 1 is less in comparison to rho 2 than rho 3. So if this type of situation is there, then heavier phase is at the bottom, the phase with intermediate density is at the center, and at the top I am having phase with lowest density. So this type of situation is there, then it is called as floating bubble or drop. Okay, so this is the situation of floating bubble or drop. In case of D, you have a solid surface. On that solid surface, some bubble was attached. Okay, and in the surrounding there is liquid. So if in the surrounding there is liquid, with reference to the surrounding liquid, density of this bubble is low. So because of the low density, it will try to rise in which direction? Upward direction. Okay, but surface tension force has kept it in contact to the surface, so because of which it will be forming this type of shape. Is this point clear? So it means that to define these shapes, over here what we are doing the balance of the surface tension forces and the pressure forces. So depending upon the balance of surface tension and pressure forces, these particular shapes are existing, considering that in all the situations fluid inertia is negligible. What it means? Fluids are not in motion. So all the fluids are stationary. Is this point clear? Now, one important point you have to consider. This is the balance of which forces I just now mentioned, pressure and surface tension. Okay. So if we have to define the shape of all these fluid particles, I have to obtain some equation which gives the balance of the pressure and the surface tension forces. Is this point clear? Now, whenever I have a substance, in this substance, if I move in vertical direction, what will happen? In vertical direction, the elevation will change. Because of elevation, hydrostatic pressure will change. Okay. And the way these shapes are there, whenever I will be moving here and there over this interface, what will be happening? The mean curvature of the interface is changing. So if mean curvature of the interface is changing, it means surface tension force will be changing. Okay. So that's why the mean curvature and the pressure gradient will be adjusting in such a way so that they can mimic this particular shape in the equilibrium situation. Okay. So how we can do this? Let us understand that this is my origin. So top point of the droplet is origin, from where actually I am measuring the value of y. Okay, at this point, if I have to consider that, say my PL at this point, pressure from inside is PL and outside pressure is PV. What will be PL minus PV at this particular point? If you see, this spherical droplet will be symmetric about this point. If it is symmetric at this point, then its mean curvature in this direction and other direction will be the same. So let me consider that mean curvature at this point is RO. Then P liquid minus P vapor will be nothing but equal to 2 sigma times R naught. All are clear with this point? All are clear? Now, if other than this I consider any other point, at this point is my curvature symmetric? No. So here I will be having two different principal radii of curvature, R1 and R2. So at this point, if I have to determine PL minus PV, that will be coming equal to sigma times 1 by R1 plus 1 by R2. All are clear with this point? And along with this, you have to also consider that when I am moving from this point to this point, I do have some change in elevation. Okay, so I do have some change in y. Okay, so to account for the pressure change with y, what I will be having? I will be having, if PLO is the pressure at the O point, then pressure at this new point PL, so let me write it as PLO. So pressure at any point L will be equal to PLO minus rho of the particle into Gy. Is this point clear? Rho of the particle, whatever fluid particle we have in hand. Okay. So do you have class after this? Maybe okay, I'll stop at this point. Time is over, so we'll discuss further in the next class then.